Hello, and welcome to the second video on probability. In this example, or in this video, we are going to look at some more advanced topics of probability. First one we're going to look at is using the words at most, at least, more than, or less than. There's an example here that's going to look at the rolls of a six-sided die. It says at least 3 out of a total of 6 would include the numbers, and then we have to fill in the blank. So let's talk about this. At least 3 means that 3 is the smallest number it could be in the set. So this would be the numbers 3, 4, 5, and 6. So at least 3 is like greater than or equal to, because 3 is the least or the smallest value it could be. At most 3 out of a total of 6 would include the numbers. Well, let's talk about at most. At most means that 3 is the highest value it could be. So if 3 is the highest value that it could be, it would be 1, 2, or 3 for our outcomes. And this symbol is like the less than or equal to symbol. The next phrase says more than 3 would include the number. So more than 3 means that the outcomes have to be larger than 3. So 4, 5, and 6. This would be like the greater than symbol. And less than 3 would be all of the values that have to be less than 3, so not including 3. So this would be 1 and 2, and this would be the symbol for less than. So you'll notice for the first two, at least and at most, they are the inclusive endpoints, and for more than and less than, they are excluding the endpoints. All right, so now we have an example here that's going to ask us to consider the experiment of tossing a fair coin twice. The sample space for this experiment consists of the 4 outcomes: heads, 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 tails, tails, heads, or tails, tails. If you remember back from the first video, we said the fundamental counting principle says that we multiply the number of outcomes for the first toss. I should have written this a little bit higher. And the second toss, we have 2 outcomes for the first, heads or tails, 2 outcomes for the second, heads or tails. So we have a total of 4 possible outcomes. And then our sample space lists all 4 of those outcomes. All right, so this one says, since the coin is fair or unbiased, the outcome of each event is equally likely, meaning that the probability of getting a heads or a tails on any toss is 50%. If a fair coin is tossed 2 times, find the probability of the event that it will land, and then it gives us 3 different examples we want to figure out. So in A, it says the probability that it will land heads on both tosses, or heads, heads. Well, we can just look at the sample space and see that there is one possible scenario, one possible outcome that is heads, heads out of a total of 4. In a little bit, we'll look at some other ways of using our probabilities. But for right now, this is the way we're going to try and solve this. Part B says the probability of the event that it will land heads at most once. So at most once means at most 1 head. So at most 1, as we talked about above, would be 0 or 1. So we're looking for either 0 or 1 head. So here is where we have 0 heads, and here is where we have 1 heads. So this would be a total of 3 out of 4. And then part C says at least 1 tail. At least 1 tail would be 1 or more. So this would be either 1 or 2 tails. So let's look for wherever we see either 1 or 2 tails. And we have the same 3 outcomes. So the probability of at least 1 would be equal to 3 out of 4. In example 4.7, it says if a young couple plans on having 3 children and the biology of gender of unborn children is ignored, the probability the couple will have 3 boys is 1 out of 8. This is very similar to the kitten example in the first video that I made, where we are looking for the outcomes of 3 unborn kittens. We want to know what their genders would be, and we made a sample space and a tree diagram. We talked about that at length. So the probability that they will have 3 boys is 1 out of 8. What is the probability that the couple will not have 3 boys? Well, this is using the complement that we had talked about in the first video, the complement would be the probability that they will not have 3 boys. So we know that the probability that the couple will have 3 boys is 1 out of 8. Using the complement, we know the probability that the couple will not have 3 boys would be 1 minus 1 out of 8, or 7 out of 8. We can expand on both of these a little bit more by using some probability rules here. The first probability rule is simplified to the multiplication rule. When the connection is the word and, use multiplication. There's a lot more to this topic if you were to take a probability-focused class. We're not in that class right now. I just want to get the basics of probability so we can understand when we're trying to figure out probabilities for future examples, what it is that we're trying to simplify for. So it says here, if A and B are 2 events defined on a sample space, then the probability that A and B both occur is equal to the probability of B times the probability of A given B. And the probability of A given B is the probability of A and B divided by the probability of B. It gets rather into the weeds. So for this class, what we're going to be focusing on this semester is basically just independent events. You'll remember from the first video that independent events means that the outcome of one event does not influence the other. And in the first video, we looked at an example of rolling a 6-sided die and flipping a coin. Those two things would be completely independent events. The outcome of the die roll does not affect the outcome of the coin toss. So if there are 2 different events, then the probability of A and B is equal to the probability of A times the probability of B. And we can ignore some of the more complicated probability rules about the given statements and everything else. So how would that affect us in the first one? Well, the probability of heads and heads. Well, if we look here, the probability of heads, heads, this would have to be an AND statement. Probability of heads on first and heads on second is what we're looking for. Well, for us to get the heads on the first, we have a 1 out of 2 probability on the first roll, right? We have a 50% chance, or a 1 out of 2 probability of getting a heads on any coin toss. And the connector AND would be multiplication. We have a 50% chance, or a 1 out of 2 probability of getting a heads on the second toss. So we can do some multiplication here. 1 times 1 is 1. 2 times 2 is 4. We could find the probability without the sample space by just finding the probability of each individual step. I should also talk for a second here about the gambler's fallacy. Many folks believe that when you do repeated gambles or repeated bets, eventually the influence of one will have an influence of another. I'll go into more detail about this in Module 5 when we start looking for, when we get into Module 5. I'll just leave it at that. Well, I guess what I was trying to say is that the outcome of one coin toss does not affect the second coin toss. So getting a heads on the first outcome of a coin toss does not affect the second or the third or the fourth or the 10,000th coin toss. It will always be the same probabilities. The second rule can be simplified to the addition rule, which just says when we use the connector or, we can use addition. So when we use the word and, we multiply. When we use the word or, we can add. If A and B are defined on a sample space, then the probability of A or B is the probability of A plus the probability of B minus the probability of A and B both occurring. If A and B are mutually exclusive, this is kind of a complicated phrase here, but if you think about what the words actually mean, it kind of makes sense. Mutually exclusive means that both sets exclude the other. So, for instance, let's say that you and your friends are hanging out in the summer and you want to do some kind of physical activity. You cannot both ride a bicycle and ride a skateboard at the same time. Obviously, you could try and do that. It might be a little unsafe, but we're talking about a relatively simple example where one set, all the people that are riding bicycles are excluded from all the people that are riding skateboards because you cannot do both at the same time. If your sets are mutually exclusive, then the probability of A or B just becomes the probability of A plus the probability of B. So we can use the addition rule, going back to example 4.6. We said in part C, what color should I choose? Maybe I'll use blue for this one. In part C, we said at least one tail. At least one tail would be, sorry, move the screen there, the probability of getting one tail or the probability of getting two tails. Well, the probability of getting one tail, just let's up so I have a little more room here. I missed this part. The probability of getting one tail would be 2 out of 4, because one tail and one tail are these two here. Or the probability of getting two tails, which is 1 out of 4, so which would be this one here. If we add these two together, we would get 3 out of 4, which was the answer that we had before. So I'm just showing how the multiplication rule and the addition rule can be applied in these examples. Then we have an example here that says an experiment consists of tossing one fair die 2 times. We want to find the following probabilities. So to find the probability that the sum is 5, I'm going to do part A with the addition and multiplication rules from above, and then I'll show a second solution for B and C using a sample space. I think the sample space is a little bit easier to understand, but it's going to show what the addition and multiplication rules do here. So, well, how can we get a sum of 5 on a fair die? Well, the probability of a sum of 5 would be getting a 1 on the first and a 4 on the second. Let me abbreviate this to the numbers. Or we could get a probability of a 2 on the first and a 3 on the second. Or the probability of a 3 on the first and a 2 on the second. Or the probability that we have a 4 on the first and what are we at? 4 plus 1 on the second. Well, the probability of getting a 1 on the first would be 1 out of 6. The probability of getting a 4 on the second would also be 1 out of 6. 1 out of 6 times 1 out of 6 would be 1 out of 36. Plus the probability of a 2 on the first one. All of these probabilities are going to be 1 out of 6 because this is a fair die. So multiplication, again, we actually color code the operations that we're doing here. I'll do all of the multiplications in pink so they stand out. And then we'll do all of the additions in a different color. So again, probability of getting a 3 on a roll is 1 out of 6. The probability of getting a 3 on a roll is 1 out of 6. Probability of getting a 2 on any roll is also 1 out of 6. The probability of getting a 4 on any roll is 1 out of 6. The probability of getting a 1 on any roll is 1 out of 6. All of these will multiply. Using the multiplication rule because of the AND statement in the middle. And then because of the ORs, we will add all of these together. And our probability of the sum of 5 equals 4 out of 36, which would reduce to 1 over 9. As I said, for parts B and C, I'm going to do a different solution here. This solution is going to be based on the sample space. Not entirely the sample space, but it's going to be very similar to that. I'm going to list all of the possible outcomes for rolling one fair die twice. Now these two events would be independent. We would roll the die once, we would record the outcome, we would pick up that die, and we would roll the die a second time. By the way, a die is just the singular word for the common word dice. So when we roll these, we are looking for the outcomes or the sum of those outcomes. So if I roll a 1 and a 1, the sum would be 2. If I roll a 2 and a 1, the sum would be 3. If I roll a 3 and a 1, the sum would be 4, and so on. I'm going to take a second here to finish filling this in. A 1 and a 2 would be a 3. A 2 and a 2 would be a 4, 5, 6, 7, 8. A 3 and a 1 would be a 4. A 3 and a 2 would be a 5. And then 6, 7, 8, 9. A 1 and a 4 would be a 5. 2 and a 4 is a 6. 9, 10. A 5 and 1 is a 6, a 7, 8, 9, 10, 11. And then we have 7, 8, 9, 10, 11, and 12. So our first probability, part A, would be a sum of 5. We would just look for all of the 5s. And that's where we got the 4 out of 36 from. For part B, I'll do this in green. The sum is even, so we're looking for all of the even numbers. So that's 1 plus 3 is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, which would be 16 out of 36. Ooh, I think I did that wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, I think I miscounted that the first time around, which would make sense because that would be half. Half of the outcomes would be even. And then the last one I will do in, let's say, let's change it up. The last one I will do in brown, just because I can. Where's brown? Brown. Perfect. The sum is less than 6. So that'll be a 1, 2, 3, 4, or 5. Actually, there is no 1s because we need to have at least 2 outcomes. So 2, 3, 4, 5. So we're looking for all of these. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which would be 10 out of 36. And then from here we could reduce this. We could divide top and bottom by 2. And we would get 5 out of 18. All right, I'm going to make a third video, which is going to go into a lot more detail on probabilities. It's not a mandatory topic of the course, but I have 3 more examples that I'd like to go over. So feel free to watch it if you'd like. Thanks for watching.